new... No, that doesn't sound right. In the start of 2021, we are starting with first principles and going back to the beginning of everything to start at the beginning. So I would like to thank the Flat Earth Professor Phil, for entering or accepting the Proof for Proof challenge. The Proof for Proof challenge is a challenge where we go over proofs and display and demonstrate the proofs that we have. Professor Phil has been very generous into entering into this. He's the only person that has so far. So this is a reply to Professor Phil's video, which will be in the description. So thank you, and onto a live recording that I did last night.
3 coplanar points, and bam, there's the radius of the Earth.
On the level.
The way I phrase it is a monument to the curvature of the Earth. It really is.
Level.
It really is.
Level.
And bam, there's the radius of the Earth.
A lot of people call that postulate 5.
Yeah.
Is it right? And
Yeah,
the fifth postulate. They call it the parallel postulate. In your particular book, though, you have 3 axioms and 12 postulates. So this is your postulate number 12. But this is what we call
Axiom 12.
What you call. Yeah, I'm sorry, axiom 12. And this is what you call the triangular axiom, right?
Yes.
I was trying to clear it up, but I don't know if I did or not.
It doesn't, if you've noticed, if you read it, it doesn't state anything about parallels within it.
No,
So
it does not.
think calling it a parallel postulate, even though it's not a postulate, it's an axiom, is the wrong thing. I mean, to me, to call it the parallel postulate means that it's wrong. There's not much of a line there. Let me see if I can give you a bit more on that.
Yeah, I'm going to jump over here and look at the
That's a bit better, isn't it?
the postulates here. Axioms, axiom 12. This is it right here. Cool.
So that's a bit better. You can see that. Now,
Yep, that looks good.
as that states, we need 2 lines to cut across this. 2 straight lines. So, I mean, we'll draw them. There's one, and there's the other. Just 2 random straight lines on this straight line. Now, it should be pretty obvious for everyone to see.
Yeah, those lines look great too. That really looks clear there. Mm-hmm.
So it states that on the side, which the 2 interior angles, it's either this angle here, or this angle here, or this angle here, and this angle here. Now these 2, or these 2 on the side, which these 2 are less than 2 right angles, it states that if these 2 lines continuously produced would meet down here. Although you can't see that, but
you can imagine that they're going to come together. Yeah,
they would be less than 2 right angles. So this means that if these 2 angles are less than 2 right angles, i.e. less than 180 degrees, then these would meet down at the bottom, and where they would meet would be the sum of the 2 right angles, would be the, what's missing from here, down here.
Yeah, if those lines were parallel, they would create 2 right angles, which would be the total of 180. However, they're less than 2 right angles, so that added angle would be down where the lines intersect. to create that totality of 180 degrees for the triangle.
So this being an axiom, it's a self-evident truth that whatever side these, it would definitely make a triangle. There's no other way you can do that. I mean, there's no way that you can have two straight lines enclosing a space. So there's no way that, because these two, if these two meet down this direction, these two get further apart. These two are never going to meet together. This line here is never going to meet itself. It's never going to meet this end. If this end goes this way, upwards, and this end goes that way, they're never going to meet each other. You can never enclose a space on this side. So this is the only shape down here. And there's this line 1, line 2, and line 3. 3 lines.
Yeah, that's just excellent, Bev, honestly, to understand this and know that it's really talking about a triangle where so many supposed great minds in history argued back and forth over this.
I wouldn't say argued. You know, people that are going to argue about this being a parallel postulate and not the same people are arguing. Exactly the same people that are going to be arguing that this doesn't state that a triangle's made on whichever side. It's something about a parallel lines that aren't even stated within the axiom. Mm-hmm. People say, I mean, there's a lot. It's very wordy. This one. It's a bit different than all of the others. Well, it's got to say a lot because this is one of the basic fundamentals of geometry. A triangle only having 180 degrees.
Oh, yeah. I mean, to me, this is great. Like, this is why Euclidean geometry is great, because you have to logic your way through this, you know. The Logos has to carry you all the way through all of these words that mean something. And then you get to the end and you figure it out. It's just great. Nothing else like it.
Right, so the other proof for a triangle is forget about that one for now. We're just making a triangle here on this line.
Okay.
Right, so you can see that. Just this triangle here.
Mm-hmm.
It's a triangle. It has 3 angles. Now, with the triangles and with the laws of Euclid that we've not actually got to yet, we've just done that basic axiom. States the triangle has 180 degrees. Well, as with great mathematical things, there's always more than one check. There's thousands for truths, right? Because wherever you end up, you always end up at a truth. So, like for Pythagorean, the one that Professor Phil went for, there's, I think at the last count that I heard of, 157 proofs for Pythagoras, because it's a truth. So what we do is, with a triangle, we take any triangle and the base of the triangle, we construct a parallel line to it. Well, how do you do that? Within Euclidean geometry, because it's a straight line, you build a perpendicular to this. Through geometry. We'll learn that later on, but you make a perpendicular to that, and then you extend this line and you make a perpendicular to that, right? So that's right angles and that's right angles, so therefore this line is parallel to this line.
Absolutely, yep.
Then what you do, because you you extend these lines because you're allowed to extend the lines, and you extend this line here and you extend this line here. Now, because of the laws of geometry, what you state is the opposite angle. So this line cuts through this parallel line, so this angle here, we'll call that double line, is the same as this angle here. And then this angle here, we'll have this as 3, is the same as this angle here. And obviously this angle at the top is a shared straight, this is a shared angle on both. So that's equal to that, that's equal to that. All of this is a straight line, 180 degrees.
Very nice. Yeah.
That's a proof that a triangle has 180 degrees. Now, in order for you to have a triangle in the first place, you need 3 straight sides. You can't have a triangle without 3 straight sides because you need to form an angle. And as we've discussed last week, or whenever, an angle is the division of a circle about radial lines, and it is the inclination of one radial line to another radial line. So you need 2 straight lines in order to form an angle, to measure an angle. Call them rectilinear angles because they are straight lines.
Correct.
Yeah, they are correct lines. Straight lines. So 2 straight lines here make this angle. 2 straight lines here make this angle. 2 straight lines here make this angle. Therefore, 3 straight lines make a shape called a triangle. The triangle always has 180 degrees. Never any more, never any less. Cannot draw a triangle with more or less angles than 180. As you noticed, right angle there. Shout out Phil for doing his Pythagorean. I might have a go at doing a Pythagoras one that's a bit simpler. Actually, are you happy with that?
Yeah, that's great.
That's good.
I love that.
Okay, so I'll give a quick Pythagorean one because I think this is also important.
You still have that number 12 up there on the screen.
Oh, right,
above
yeah,
you.
sorry.
It doesn't really matter too much.
Yeah, it's cutting off the screen down though, isn't it?
You just wouldn't want to confuse somebody, I guess.
Yeah. Well, people get easily confused. I don't even know where it's gone now, though. Oh, come on. There you go. Right. Get rid of that.
Yep, it's gone.
Here is Pythagorean triangle. In order to draw a Pythagorean triangle, what you need, or you must have, right angle. So go upside down.
If you could play around with that water level too, that's always great. Whenever you get a chance.
Toys, they call them.
Yep.
On Twitter, they call them my toys. Oh, that's not going to work like that. It's in the wrong place.
Makes me think of one of those little globe toys. That's what I call a toy.
Yeah. These are practical toys. So this one is. It's a bit of a toy.
Yep.
Is that? That's messing us about, isn't it? Right. So, if we have a triangle. It's going to be... I'm not very good at doing this. But first off, step 1, right angle triangle. Now Pythagoras is used to find the right angle usually when you're practically using this. But you practically find it because of this principle that we're talking about now. So Pythagoras states that a squared plus b squared equals c squared.
Mm-hmm.
Everybody's heard it. But
Oh, yeah.
what it actually means is we'll call this side A, and this side B, and this side C. So a squared seems like a mathematical function, but it's not. It's literally a square. So what you do is you build the area of this square with this. So these are the same. So this is a
square.
A square.
Mm-hmm.
Built from this side of the triangle.
Mm-hmm.
And then b squared is similar.
I like that little square indicator, the 90-degree angle square. Mm-hmm.
And then the area of this square plus the area of this square equals the area of this square.
Mm-hmm.
So
that's amazing.
That is how you construct literally a Pythagorean triangle, and that is all based upon, as you'll notice, it's based around this right angle here, but around it there are the right angles everywhere. Right, this principle of Pythagorean triangle wouldn't work without this. Not just this one right angle here, but every one of these right angles make this formula Pythagorean work.
Yeah. John in the chat over here said, interesting, never looked at it that way before. Isn't that amazing that in school you learn a squared plus b squared equals c squared? And they never show you this? Why is that?
Yeah, the logic flows through it, and it becomes much simpler when you see this like this than it does when you're in school going through this the process of, I think personally, the process they go through at school within mathematics is to make this seem complicated.
Mm-hmm.
This is a logical process that should be very, very simple. But
yeah, they take away that logic from it and just give you an equation, and you just think it's math. You don't understand it without this, right? Not fully.
Yeah,
not in a way that
they've took the logic. They've took the logic of seeing this and your brain processing this and going, that makes sense.
Right.
They've took that away and left you with this that doesn't really. I mean, if you were taught that you don't understand mathematics because all you see is letters and numbers, and what the hell does that mean? It's crazy. I don't understand that. Some sort of code. Well,
yeah, it's the what. They give you that what. Okay, but like Right the Hand talks about, they don't give you that why or that how. And when you see it this way, you go, yep, that's what it is because of that. That just blew me away. When you first showed me that, I was like, oh my God.
I wouldn't exactly call this a proof either. Right? This is just an explanation of how it works. Unless you were to draw this out and actually construct these squares, and then take these squares and try and place them in here by cutting them to make sure that this square plus this square actually equals this square, then you could say you've gained a proof. But just drawing this out and saying that's how it works isn't actually even a full proof.
Mm-hmm.
You need to do some work extra on top of this. Now, this proof is pretty simple, or it's easy to get your head around. Can you imagine trying to do this as Pythagorean with Euclid? That's going to be something amazing to go through. That proposition 47, pure geometrical Pythagorean triangle. So
whenever you want to, if you want to do it now or do it later.
We're doing it on the course. We will definitely do it on the course because it is sublime. But you need to get a grip on the geometry before we get round to the Pythagorean proposition 47. That's crazy.
Yeah, I would like to go over some of that course with you later on today. It's pretty intense. Yeah, we definitely need to.
Well, I'm not going over it. I'd be quite happy to spend 11 weeks going over the whole course. Just to make sure we're getting everybody up to speed. I'd go 2 or 3 weeks on the beginning bit. Keep going backwards and forwards through it.
Certainly, there's no rush. Yeah, no rush at all.
Have we done the board? Or did you want to do anything else?
Is there anything else you want to do on the board? I don't know. What do we want to do? We don't want to get into book 3 proposition.
I gotta say, you're totally blowing my mind right now.
You twat. How do we know the Earth is not flat?
We don't. It's flat.
That was that.
Understanding of the world in which you live, then of course the world looks flat. The world looks flat. The world looks flat.
Neil,
Bitch. You twat.
I gotta say, you're totally blowing my mind right now.
That's what I do. 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 What I do.
But I don't have much patience for anyone who denies that this challenge is real. We don't have time for a meeting of the Flat Earth Society. Flat Earth Society.
My friends, these people are so out of touch with science. You don't need to be a scientist to know that the Earth is round.
They must have been founding members of the Flat Earth Society. They would not have believed that the world was round.
Like water. Now you put water into a cup, it becomes the cup. You put water into a bottle, it becomes the bottle. You put in a teapot, it becomes the teapot. Now water can flow or it can crash.